we would like to find the centroid of a region in the first quadrant bounded by the curves y equal f of x, y equal g of x from A to B with density delta of x. Density purely as a function of x. The most important thing is to always start by finding the area. Even though we're not interested in the actual calculation of the area, it sets the format for all of the other things we have to find. So we know the area is simply the integral of f minus g from A to B. Now with that, we then know that the mass is the density times the area parameter. The moment related to the y-axis, that involves the x distance, is the mass times the x distance, and the moment to the x-axis, which involves the y distance, is the average of the functions times the area times the mass. So with that, we can set up any problem in the xy plane. Now, our ability to integrate the problem clearly depends on the complexity of f, g, and delta. So assuming that those are not terribly complicated, we should be able to find the centroid of pretty much anything. So let's look at some examples. All right, we would like to find the centroid of the region bounded by y equals x squared, x equals 0, y equals 8 minus 2x in the first quadrant. With density x squared. Okay, now this is not terribly complicated because our boundaries are simple polynomials and our density is a simple polynomial, which means our integrations will also be simple polynomials. So the first thing we want to do is sketch a fairly accurate region so we can get our boundaries correct for the integrations. So we're in the first quadrant. We're bounded by the parabola, the line, and the y-axis. Now with that, that means our region is entirely in the first quadrant. And in order for us to be able to find the area, we have to make sure we have the correct boundaries once again. Now I need this point right here. So if I set these two equal and solve, I'll find that that ordered pair is simply 2, 4. So the first thing we're going to do is express each of our integrals. So the integral for the area, okay, that would be from 0 to 2. Now, think of the area. I have to go top curve minus bottom curve. So it would be 8 minus 2x minus x squared dx. Okay, I'm not going to bother calculating that, but again, that's the foundation for all of our integrals. So our mass integral will be the same integral with the density inserted. Okay, the moment related to the y-axis. Okay, same integral, but multiplied by x. And finally, our moment related to the x-axis be the same as this integral, again, but multiplied by the y distance, which is the average of these two. So I'm going to add them together. And then multiply it by that. Okay, so these three are the integrations we want to perform. So we'll go ahead and do that next. Erase this. And I'll restate each one of them one at a time. Okay, now off to the side, I'm going to go ahead, because we're going to find these one at a time. And I'll state our results so we can remember what we actually did. So the first integral we're going to find, again, is the mass, which we just stated a moment ago. So if I go ahead and distribute, that will be the integral of 8x squared minus 2x cubed minus x to the fourth dx. Again, a fairly simple antiderivative. 8/3 x cubed minus 1/2 x to the fourth minus 1/5 x to the fifth, evaluated from 0 to 2. And then just using the fraction key on your calculator, evaluating this straight across, we get 104 over 15. So our first result here, 104 over 15. Okay, I'll go ahead and do the y moment next. So this one here, we said before, basically will look just like that integral, but I have the additional x multiplied in. So then that one will be basically x times this, 8x cubed minus 2x to the fourth minus x to the fifth dx. Okay, and then that would give us here 2x to the fourth minus 2/5 x to the fifth minus 1/6 x to the sixth, evaluated from 0 to 2. And we see that, again, using our calculator, that would be 128 over 15. So we'll put that one up here. Okay, now one of the things you notice in general is that the numbers themselves are not always very friendly, because when you integrate polynomials, you get a lot of fractional coefficients. So we're not expecting pretty integer answers. That's probably artificial and not really to be expected. Now the last one, probably usually the messiest of the bunch, and that'll be the moment to the x-axis, which would be the integral from, again, 0 to 2. And now what I'm doing is I'm taking the mass and I'm multiplying it by half the sum of those. So that one there, after I distribute, comes out to be 32x squared minus 16x cubed plus 2x to the fourth oops, lost my place there for a moment, minus 1/2 x to the sixth dx. Double check that one. Yes. So when I perform that integration, that's 32/3 x cubed minus 4x to the fourth plus 2/5 x to the fifth minus 1/14 x to the seventh, and evaluated from 0 to 2. And when I get done with that guy, that one's not quite as friendly. That's 2624 over 105. Yikes. So 2624 over 105. Now, we're done with all of the complicated work. Now we just simply have to express the x and y coordinates. So if you remember, x bar is the y moment over the mass. And again, the y moment is the distance to the y-axis. That's why that's where x bar comes from. In this case, that would be 128/15 over 104/15. So if I use my calculator and I reduce that, that comes out to be, I believe, 16 over 13. Y bar, which is the moment to the x-axis this way, over m, and that'd be 2624 over 105 over 104/15. That one not quite as friendly. That's 328 over 91. That's a little less than 4, okay? That's a little more than 1, that's a little less than 4. As it turns out, if my picture is fairly accurate, we're more than halfway across and not quite up to here. So that probably puts us right about here, which is reasonable, because if my density is x squared, that means the density is increasing from left to right Once I exceed 1, the density starts getting greater. So that means that the mass should be a little bit more in that direction. So my final answer basically is to say my centroid is the point 320, 16/13 over 300 and 328 over 91. There we go. Not very pretty numbers, but nothing terribly complicated in the algebra. So this would be a very, very generic type of problem. Now we're going to do something a little more geometric. Now, in geometry, there are certain shapes where it's very easy to find the centroid. And I'm talking about a shape. For example, if I simply drew a rectangle, okay, let's keep it really simple. If I had something like a rectangle, this is a shape. This is not a solid object. There's nothing in the middle. If I wanted to find the centroid of this, the balance point, all I'd have to do is take the diagonals, and where they intersect, I know that's the centroid. In general, a lot of the quadrilaterals, it's very easy, particularly squares and rectangles. All triangles is easy to find the centroid. All triangles, the centroid, if I just made a generic triangle, the centroid is the intersection of the medians. A median is midpoint to opposite side. So if I did this, okay, there would be my centroid. This goes back to, again, to high school geometry, if you could remember some of these things. What we want to do is calculate the centroid of a geometric shape that doesn't have any mass because there's no density. It's just, I want to talk about the outline. Now, how do you use calculus if there's no mass? Well, here's the easy way. If I took a shape, let's take the last example that I just did. If I said the density was constant, or what we call uniform density, then it's not getting denser as I move left to right. It's always exactly the same. It'd be like a piece of wood that's the same all the way through, no knots. So if I think of it that way, having a shape that has no mass and having a shape that has constant density, it's really the same sort of thing. The density does not affect the final answer. So what we do in a massless object is we just simply say it has constant density. And the reason is, otherwise your mass and your moments would all be 0 because your delta would be 0. And you'd basically trying to find a centroid with all of your numbers being 0. That's not very effective. So let's consider an equilateral triangle. Now, if I have an equilateral triangle, if you remember, that means all the sides are the same length. And so if I was looking at the intersection of the medians, I'll do the best I can. Again, this is free-handed, so it's not going to be perfect, although it probably won't be too bad. Yeah, not bad at all. The intersection of my medians is right around there. So if I'm looking at it as I move from bottom to top, I'm not quite halfway up. Clearly, I'm more in the lower half, but it's hard to know exactly how far that is. Now, we can use algebra and geometry and combine them, but I would like to actually calculate. So let's find an equilateral triangle, how about of side A? An equilateral triangle where every side has length A. Now, the key is, to make this work, I want to do it on the XY plane, but I want to set it up in such a way that it makes it very easy to describe my boundaries. So we're going to do it like this. I'm going to put my equilateral triangle like this. Okay? I'm going to put it so that it's perfectly centered on the x-axis so that this is vertical right here. Now, if each side measures A, one of the things we know about an equilateral triangle, and I'll remind you in case you forgot, that's where the 30, 60, 90 triangle comes from. So if that side was length A, then that piece would be 1/2, oops, sorry, this piece would be 1/2 A. I'll put it right here. That would be A, and this would be √3 over 2A, if you remember, the 1/2 to √3 over 2 to 1 ratio. You remember that from a 30, 60, 90 triangle. So if I'm setting this on its side, if that distance is A, then that distance is only 1/2 A. okay? This would be then negative 1/2 a. So then what's this distance? That'd be root 3 over 2a. So now I have a situation where I can describe the equations of the lines passing through these rather simply. Since it's going through the origin, my slope would be 1/2 a. I'll write it here. My slope would be 1/2 a over root 3 over 2a, which would simply be 1 over root 3a. Or if you want root 3 over 3, it really doesn't matter. And here, similarly, my slope would be negative 1 over root 3a. So that definitely makes it easier. So that means the equation of this line would be y equals 1 over root 3a x. And this line would be y equals 1 over root 3a, negative 1 over root 3a x. Well, that definitely makes this easier. And I'm going from 0 to root 3 over 2a. So let's go ahead and set up our area first. Because we said if we can set up the area, then the rest of it works out quite nicely. So the area would be the integral from 0 to root 3 over 2a, top curve minus bottom curve. So that would be 1 over root 3ax minus negative 1 over root 3ax dx, which is simply 2 over root 3ax dx. Okay, so if I wanted to find the area of the triangle, it would simply be that integration. So now the next thing we want to do is do the mass and the moment setup. So the mass, now how do we do the mass? We said this is just a shape. It has no density. So what we're going to do is say, all right, let's say our density is k, where k is just a constant. And what's going to happen is the k will end up factoring out of the problem. So if I said it was density 1 or density 1 billion, it doesn't matter because the density is constant. It's not going to affect how I do my integrations. So the mass will be k 2 over root 3ax dx. My moment to the y-axis will be kx 2 over root 3ax dx. And then my moment to the x-axis, now this is going to be a little bit tricky. Remember, I want to take half the sum, but when I add these together, I'm going to get 0. So this is going to be the integral of k times 1/2 of 0 times root 3, 2 over root 3 ax dx, which is clearly just 0. Ooh, that definitely makes my life a little easier. So I really only have to do these two calculations. So let me erase this and we'll do this again. Okay, so the mass calculation, all right, we said that was 0 to root 3 over 2a. Okay, I'll write it down myself. And that's k times, where are we here? K times 2a over root 3x dx, which is ka over root 3x squared from 0 to root 3 over 2a. And that turns out to be exactly k root 3 over 4 a cubed. Now that looks kind of scary, but remember, a was the length of each side of the triangle, so we would have a number there if we had a specific value of a. Okay, let me get rid of this part here. Now our moment to the y-axis, which looks just like this integral, except now I'll also have an additional x, if you remember, because it's x times this. So that would be the integral of k 2a over root 3x squared dx. And that will be k times 2a over 3 root 3 x cubed from 0 to root 3 over 2a. And when I evaluate this and I cube this, all of the 3's turns out are going to cancel. And I get simply k over 4 a to the 4th. Again, because when I cube the root 3's, they will cancel with these. I'm going to cube the 2. Boom. Now we're ready to answer the question because we already said that mx was 0. So at this point here, we can clearly state our moments. Excuse me, clearly state our centroid, our x bar and our y bar. This part I like because it didn't matter that the density technically was 0. We said it's constant. It doesn't affect anything. So x bar, y bar. So x bar, if you remember, is the my, which is the k over 4 a to the 4th over what we said was k root 3 over 4 a cubed. And that turns out to be 1 over root 3 a, or if you want, root 3 over 3a. We might find that last form a little bit more useful. Y bar is 0 because mx was 0. Now here's one thing I love about this problem. That answer looks really, really scary. Well, actually it's not. This distance is root 3 over 2 times a. Our centroid is root 3 over 3a, comma 0. Root 3 over 3a is exactly 2/3 of root 3 over 2 times a. So if you're looking at this picture, I'm exactly 2/3 of the way along the x-axis till I get there. So if you go back to our original picture, this coincides. Remember, we said it was less than halfway to the top? It turns out, if I stand up my equilateral triangle, it's exactly 1/3 of the way from the base to the top, which is beautiful. We proved a geometric formula using the calculus of centroids.